Thanks for being here with our special interest group webinar workshop for geotechnical analysis for July 2019. And today we're talking about the command line and scripting of automated model definition. Quick overview of what we're going to discuss here. Why do we need automation? Then we'll show why we need the Plaxis command line for this. And then the first automation option that we'll do is a simple macro option. But we'll see that macros will have limitations, so that's why we'll go to scripting and Python scripting in this case. And so that's what we'll use for the session here today. If we want to go beyond the standard command line, we'll have to go with scripting. We'll show this in a demonstration using the parametric geometry for slope stability. So I'll build this script live and we'll see how it works. Then also show an option to share your scripts with colleagues, and some colleagues might not always be into programming, or they might be afraid of it, or they think they don't have time to learn it. In that case, we can just prepare a script and we can share it with the colleagues, especially if you've made something nice that's very efficient and it increases productivity within the team, then it's a good idea to share these automation tools. Why do we want to have automation? Now, when you do actions that do have a repetitive nature, of course, we don't want to redo the same thing over and over and over again, because that's a waste of energy and a waste of time. But it also can introduce human errors because you might be tired. You might then click on the wrong action, or you might copy data in an incorrect way. So that's always a good idea to make sure that we can have the automation can take care of those kind of things. So it can be redoing the same action and input. For instance, we calculate the Plaxis model and then we automatically save it. Plaxis doesn't automatically save your model after calculation, but you can automate that by just doing calculate and save. We might want to reuse data from other sources. Maybe you have data in a database or an Excel spreadsheet that you want to reuse without retyping all the large amount of numbers. Maybe we want to run multiple calculations overnight, so we don't have to manually load the problem and then run the calculation automatically and then save it and then start the next one, which if you want to do that overnight, then you have to be in the office to do that. So we can also automate that. Maybe you also want to do an optimization of parameter design. With automation, we can also do those kind of things. Another option why we need automation is if you want to get the same standard structure of results to use. Maybe you have special reports or Excel spreadsheets that you want to put data in a specific format. With automation, you can retrieve the data from Plaxis output, and then we can put that into a spreadsheet or in a report. And today we're just going to cover the Plaxis input program, but the Plaxis output program is also you can also automate that using Python scripting. Also, if you have to do analysis that requires more of the same thing, you can think of parameter studies. Maybe you want to do something on sensitivity. Maybe you want to do some probabilistic analysis. Then we can use maybe Monte Carlo simulation. And we can just have a stochastic input of your parameters, which randomly selects a value from the distribution and then runs a calculation with that, and it does that for multiple times. So we can quickly do these Monte Carlo simulations. You can also extend that a little bit further, and maybe you want to do back analysis or connect it with the observational method in which you will use monitoring data to optimize the soil parameters, that you can sort of better predict what's going to happen in the next stages. So those are good ways to include automation for that. Also, once we're inside the program, we cannot automatically get data quickly out of it in an automated fashion. But when we introduce automation, we can. Maybe we want to interact with an online database. Maybe you want to send notifications to your phone. Those kind of things, it goes beyond what we can do with the standard Plaxis application. So before we think about automation, it's good to realize that the command line that we have in Plaxis, it's the center of all automation. Anything that we do with the Plaxis application that changes something on the data structure, that will be converted to a command. So if you do something, clicking with the mouse, selecting things, selecting something in the selection explorer, and then change, for instance, load values, generating the mesh, run the calculations, everything that we do, it will all be transformed into a command, And you can see them also always appearing in the bottom of your screen in Plaxis input. And you can also see it here in this slide, where we'll see that we have the command line showing the, we added a phase here, we changed it to a different current phase, we changed the name of the phase, and deactivate some soil in this phase tree. So with that we can automate that, but it's also a good way to inspect what's happened in the model. Now, if we go to the help menu, there's a very detailed command reference, and all available commands and syntax is available there. Now if we look at a simple command, if you sort of look at what the structure is, what are the ingredients for a good command, of course we need to have the command name, otherwise we don't have a command at all. And then the command needs to perform an action on something. This is what we call the target object. In this case we want to rename point 1. And we have to tell this command what kind of parameters it has. In this case it will be my point. So we will have to rename point 1 to my point. And these are the parameters. Now if we look a bit ahead, when you go to an object-oriented programming environment, like Python for instance, this would change to point1.rename, and then in brackets here you see my point, which is the parameters what we can find here. But okay, the command actually is going to have the command, a target object, and a parameter. If we know how to write commands, we can execute more than one command quite easily. So in the expert menu, we have an option called Run Commands. We get this box here, which is the commands runner, and we can input a series of commands quite quickly, just line by line by line, and then we can execute them all at once. We can, for instance, in this case, just copy paste command logs, or we can open a file with a command log in it. Or if you have, for instance, prepared commands in your Excel spreadsheet, we can also just copy and paste these commands from Microsoft Excel, for instance, into Plaxis, and then we can automatically run all those commands that's been generated. We can also reuse a series of commands. Of course, you can sort of copy and paste these commands over and over and over again, but that makes sort of a hassle. We can also store these as a series of commands as a simple macro inside Plaxis input. It's available in the expert menu as well, just below the Run Commands option. And macros can also have keyboard shortcuts. So if you like to work from the keyboard, then we can just use this Shift Control Alt plus a numerical value that corresponds to a specific macro. So I will show two examples. One will be to just recalculate the model and save it. And the second example I will show directly afterwards is that I will change all uncalculated phases to use updated mesh and then save 20 steps per phase. So let's start Plaxis 2D. I already loaded the model. Now here we see we have a few phases along with the construction of an embankment. Now in the expert menu we can here find the Run Commands option, and of course we can, for instance, type this option that I saw, go to stages, then I say calculate the model. Calculate would be then the command, and then I would automatically save this one. So I can of course run everything here, but yeah, probably I want to store this one and reuse it multiple times. So I'm just going to remove it from here. We're going to move here to the expert macro library, manage macro library. I'm going to here add a new one. I'm going to paste the commands and I'm just going to call it calculate plus save. Go to stages, calculate, save. These are the three commands that will be executed. And now I'm going to expert menu, macro library, and you can see here we have a new macro, calculate and save. I can use a keyboard shortcut, but I will just click here and we'll see what happens. You can see the commands runner is actually launched for this, and it will execute all the commands in this one. Now it will run all the calculations for the different stages. I'm just going to cancel the calculation here because I think we're not interested in the results, we're just in the mechanism of running these automated commands. So I'll just here stop. And then we want to stop calculating. Yes, we do for this case. And what we'll see that after the calculation is done, it will also automatically save the model. So if we make this a bit bigger, here we go. So we can say, go to stages, I did, calculate and save. Now maybe we want to extend it, maybe we want to, because this takes just all the commands that have been calculated. I want to just calculate all and save. Now what I can do, I can use a command called apply, and I have to apply this on all phases. Then I have to use the set properties command. Basically, the apply will run the next command. That's the first sort of parameter of this item here. It will apply this command to any of these items which are in this list. In this case, it will be phases, so it will be all the phases. So to apply phases, set properties, and if I want to set everything to be calculated, I will should calculate, and I will set this to true. So basically, it will change the properties for all the phases in this list, phases, and then it will change the should calculate option to true. Okay, let's see that and let's see how that works. And then we're going to say macro library, calculate all and save. And you can see here it starts to recalculate everything, because what it first will do, it will first change all the phases to set to be calculated. So it is with this should calculate true. And then we will fire the command to calculate all phases. So that's this macro. I also will stop this one. So you can see I already extended the macro a little bit to have something more fancy. Now another option what we can do, I'll just mark all the phases for calculation. Another example I wanted to show is I'm going to directly write this macro here, and I will call set to updated mesh, we call it. And for this one, we want to set all the phases that are still not calculated. We want to change them to use updated mesh. So in this case, we need to figure out a way to make sure that all the cases which are not set to be calculated, that they are marked for that they are being changed such that updated mesh is activated, and also we don't want to change all the phases which are already calculated. Now we can have a special option called group filtered, which is a command which can group items based on a certain criteria. So it's called group filtered, and we have to do that on all the phases. And we have to specify, of course, a condition. Should calculate should be set to true. So this is the should calculate is the condition that we have. Next is we also want to make sure we cannot change it for the initial phase, and we don't want to get an error message for this. So we get group filtered, and we do this on the last created groups. Groups is the collection of all the groups that we have, and within this square brackets here we can refer to the item which has been just created. So this is the last created item. So this basically calls indexing of these items. It starts counting from 0 up until the last created item. But if we add a negative index here, it will start counting from the end of the list. So basically -1 means the last one. And the condition that we have here is that the internal number should not be equal to 0. The initial phase has its internal phase number set to be 0. So here, with this one, we exclude the initial phase. Now, what we want to do, we want to apply on groups -1. Now, groups -1 is again the last created group, which is not the same as that one that we use here, because in this case we also create a new group based on the condition that the number should be not equal to 0 and that it still should be marked for calculation. So we can do apply groups -1. We have to use the set properties. The shorthand form of that is SPS. So we can also use the shorthand form for the set properties command, which makes typing a little bit easier. And we want to make sure that we change the use updated mesh, use updated mesh, and the value that we want to set is true. Since we're using Plaxis 2D, we also want to use updated water pressures. So this is for 2D only. And what you want to do, let's copy again this one. And we might also want to change the max steps stored to be 20. Now if you run this, what we'll see happening is that we create a new group that contains all items which are still to be marked for calculation. Then we create a second group, a temporary second group that we just need to make sure that we can exclude the initial phase. And then we're going to change some properties for all the items in this selected group. But of course at the end that gives us 2 additional groups, and if we run this command several times, we get a lot of groups in the model, which of course we don't want to have because these are just temporary groups. So what I will do, if I use these temporary groups, I'm just going to ungroup groups -1, and I'll do this again for the second time. So with that we can sort of ungroup this. I'll comment them out so you can see why we would need to add these ones. Okay, so here we have this command. I will set OK. I'm going to export, and then what I will do, I'm going to go to the macro library and go set to use updated mesh. And you can see here it applied group filtered phases, which created a new group containing 5 items. And we have 1, 2, 3, 4, 5 phases, so that fits. Then we made a group filtering on this last created group, but we don't want to have the initial phase, so we're back at 4 phases. And then we set the use updated mesh. So let's see if that actually worked. You can see here updated mesh, updated water pressure, both activated, and the max number of steps stored is set to 20. If you go to the next stage and the next one and the next one, it's all there. So you can see it already saves some time because I don't have to check all the phases and go for that. And what I mentioned about the groups is that we have these 2 additional groups here. Now say that we don't want to have these. So what I will do, I'll just reopen the same model again, so you don't have the here we go. So we see that we have the here. Let's see, we don't have updated mesh yet. The updated mesh here is switched off, and updated water pressure is also switched off. So what we can do here is that we can then go back to the macro library, and I will just here I'm going to include this one. So I'll remove the comments. So anything that you add this hashtag character, will be considered as comments for the Plaxis command line. So that can also help you to structure better your item here. So let's rerun this macro, the macro library, set to updated mesh. It runs here. If you look at here, we don't have any groups, so we keep the model quite clean. And what we see here, when we use updated mesh, these options are activated. So that's a good thing. We quickly can change this. And you can imagine if you have a more detailed embankment construction that you want to model, we can quickly change 20, 25, 200 phases depending on, of course, how many phases you have. But you can quickly change everything here and do a quick variation of all of the analysis without checking all the phases and developing some relative strain injury for clicking all the items. So that was a quick look on the macro functionality. So this commands run and macros is great for repetitive commands, and it's easy to set up a list of commands in a text file or a spreadsheet, and we can just copy and paste everything there or run it from the log file and quickly run this. But there are, of course, some limitations. There's not much interaction with data. We cannot use, for instance, the result of an analysis and based on that add another phase. For instance, if the excess pore pressure in a consolidation phase has not reached a certain level, that we add another phase or something like that. So that's not possible. The results that we generate, they are only available in the command line session, so we cannot sort of do anything outside of that. For instance, if you want to reuse it, for instance, based on the result, you want to add a new phase and change the load value, we cannot do that. So we don't have any if statements, for instance, or loops. We cannot have reuse the values or have some kind of arithmetic expressions to do that. We also cannot use external libraries, and we can also not directly export to files or spreadsheets using the command line, which of course is a bit of a downside of this. But fortunately, we can move to the next step for automation, which is basically the use of the remote scripting server inside Plaxis. So we can start the remote scripting server. You will see the window here popping up, where we have to say, okay, on which port can we communicate with Plaxis. We also have an encrypted communication line between your Python environment and your Plaxis application to make sure that the communication is safe and secure. So with that, we can initiate that Plaxis will act as a server to receive and answer to specific commands. Then we're going to use the Python scripting, and you can see a few of the first lines here that actually, which I'll also show in the next slide, is basically these are the instructions to start communicating with the Plaxis programs. So we have some boilerplate command that that you can just add always. So we have to import the Plaxis plxscripting.easy library, so we can quickly reuse the options in the program. And then we have to set up what we call a new server object from this plxscripting.easy library. It has three parameters: the local host, which is basically the PC that you're running Plaxis on; the port number, which you assign the communication over. So it's the same. If I go back one slide, this is this number here. It's the port number that is specified, and also we have to configure the password, which is also here a parameter. If somebody looks at the Plaxis documentation on Python scripting, we have a convention here. If we have s_i, s refers to the Plaxis server object, and g_i refers to the global object of the current session. Basically, this means the open Plaxis model that you're currently dealing with. Also subscripts that we use. If you use _i, it refers to input, and if it refers to _o, it refers back to output. So that's sort of the convention that we use in our Plaxis documentation. Now, if we go look beyond in the autonomy of a command, is that we have this rename point1 to my point. If we go to Python, and we have to sort of this target object, we put it first, then we add a dot, then we apply the command for which it's being used, and then we have the parameter here for my point. So with this option, we can rename point1 to my point. So this is slightly different from the command line. So if we look back to look at some different commands. So for instance, adding a borehole in Plaxis 2D requires the borehole command and the x coordinate. And we can also, in Python, we have g_i.borehole and then between brackets 5, because that's the input parameter for setting up the borehole. If you want to add a new point, it would be, the command line would say point12. In Python, it would mean gi.point and then the parameters are 1, 2. So the x coordinate first and then the y coordinate. If we want to change the coordinate for point 1, then point 1, we have to say set point 1.x to 2.3, for instance. Now in Python, it would look like gi.point1.x, and then we do not as an equal sign here because we're dealing with programming. This is an assignment, so we set the assignment for point 1.x to 2.3. We can also use the set command, but this is the preferred way of doing this. One of the tricky things in the input of the materials is the input of materials. If we generate a new material dataset inside Plaxis to the input, Plaxis will generate a command that will include all the available parameters, even if they're still set to the default values. So you can see very, very long commands being generated. Now, there are also shorthand versions in which we only have to supply the minimum amount of parameters being used. So on our Plaxis website, we also have a page in which we highlight these required parameters. But say that we want to use a more column material dataset, what we can do here, this is the command. This is the minimum command that we need to set up a valid material dataset. So the command is called soilmod. Then we have a parameter material name, which we have to give it a name. In this case, we call it clay. Then we have another parameter, which is the soil model. We set it to 2. 2 refers here to more column. If you want to, for instance, use the hiding soil model, we can use 3. If the H is a small model, we can use 4. So on the web page that we have, we can see for all the different material models which number is the equivalent here. Then the material datasets usually require the input of a shear modulus and not a Young's modulus. Fortunately, with Hooke's law, we can convert the Young's modulus to a shear modulus just by with the formula of E is gref is E divided by 2, 1 plus nu. So we can give here our Poisson's ratio nu to 0.35, and then if we want to put the undrained shear strength or cohesion, that's both referred to cref. In this case, we give it 50. Now, if we want to do the same thing in Python, we can have these clay parameters. So we first set up a list of these parameter name and its value. So here is the material name clay, the soil model set to 2, the shear model is set to 5000, the Poisson's ratio is set to 0.35, and the undrained shear strength set to 50. And then we're going to create the material, and so we have here the gi.soilmod command, and we do here what we call in Python is the unpacking of this list. So we can actually send these parameters to Plaxis quite easily. And what Plaxis then returns to the Python environment is that it will give an object back, which is the newly created material dataset, and which we can assign it to a variable in our Python environment. In this case, we call it clay_mc. Okay, so that's the basic things. There are more details to that, but I think this is a good way to start. In this case, I'm going to do a quick demo. We'll do a Python script on slope stability. So it's a slope stability problem. I will show the steps how to design a parametric script, because it's nice that we can have some kind of very simple input that we can just quickly vary some parameters and get different results for the case that we want to check. So we also set up the Python script, and we're going to actually run the case here all live. So for slope stability, Taylor made some publication showing stability number versus depth factor charts in a publication from 1948. Actually, it was just an undrained shear strength slope stability type of problem, and so he had some basic input for this. He had the height of the slope angle here. In this case, we set 1/2. Then we have this parameter L, which is basically the layer thickness. And then this layer thickness has also an undrained shear strength. and of course a self-weight. So this is 20 kilonewton per cubic meter. And also we put here the another soil layer beneath, because that's more easy for fine element calculations to have just a more flexible layer at the bottom rather than a very rigid boundary. So in this case, if you look at H and L, if we assume these are 12 and 16 meters respectively, then our depth factor will be 0.33. Now if we look at the chart here, 0.33 is here, then we move up until we find, and these curved lines here resemble the slope angle, so we should be roughly halfway between these lines, and then we go to 0.15 for the stability number. And based on the stability number, we can calculate the factor of safety. And with the factor of safety, it's calculated as the underlying shear strength divided by the unit weight of the material. H is the slope height, and this N naught factor. So this gives us a factor of 1.39. So let's see where this will give us if we're going to put this to Python scripting. So if you think about this as a parametric tool, there are a few inputs that we have. If we look at the slope, we have the h, so the height of the slope, and we have the angle, which is 1 over x. Well, so this, in this case, 1 over 2. Then the soil layers that we have the parameter L, which is the thickness of the soil layer, and we have underlying shear strength and self-weight. So if we want to do the demonstration, what we're going to do, we'll start with some start Plaxis 2D, and then we're also going to launch an editor. In this case, I will use the Site editor because it's bundled with the Plaxis program, but of course you can use your own editor if you would like. You just have to make some steps to make sure that it connects with the Plaxis distribution. Okay, so we'll start with the new model. We'll start this one from scratch, and from the expert menu I can here, for instance, here in Python, choose to start the editor. As you can see here, I have to configure the port. It's set to 10,000 and configure the password. I'm just going to copy it here because I will need it later on. And I'm going to start the server. You can see here we have all green check marks, so we're good to go. Close this one, and you'll see here we have started the Site editor, which is a enhanced text editor with special functionality for Python. So that's quite easy to use. I'll just put this one here, and then I'm going to put Plaxis 2D next to it. Let's see, where's my Plaxis? Here we go. So we can see the progress of this. I already prepared a bit of the part of the framework of this, but I will still explain steps. So I will have some input parameters. We have the slope set to 2. I have the parameter d here, and d is actually the h actually that we use from the presentation. So I'll just quickly change the h here in my script as well. And we have the parameter L for the top layer, which is in this case 16. And then we can set, and then here we have the input for the top layer. In the Plaxis scripting requires that our material names have a name. So we're also going to add this one here. So we give it a CU value. So this is our underlying shear strength, a gamma for the soil weight. The L refers to the layer thickness, and then we also have a Young's modulus set to 5000 kilopascal for this case. The bottom layer, we also going to add the same thing, which has a layer thickness of 5. Then of course I have to show that we're also going to start the boilerplate. In this case I have the PLX scripting.easy import everything from this module, and then I will assign the SI and GI variables here by using the new server. I have the localhost the port number 10,000, and I have to set the password to the one I just copied. So I'll just copy it to make sure I use the same one. So that's good. Then we'll start by building the geometry. Now in this case we have the slope and the top layer. We have to define that we can use a soil polygon to generate this one. So we have the width and the height that we have to consider. That's for the slope. It's quite easy because those are the input. We give directly the parameter h and the slope here, so that's easy to do. Then we also have to specify the boundaries on the left and right hand side. In this case I will just assume that that this side of the model will have the same width as the width of the slope, and also do it the same at the other side. So by that we'll ensure that any failure mechanism will be fit in the model. And that will generate, if we do that, it will generate with the polygon command, it will generate a new polygon, and it will also generate a new soil object, which is basically the soil user feature of the polygon. So it will generate two new objects. We'll do the same thing for the bottom layer. It will have the same width as the top layer, of course, because then we have a compatible model, and also it will generate polygon and soil polygon. So back to the Site editor and our Plaxis 2D. So I set up already something here. I will call a determined factor of safety. So we'll give the h, slope, top layer and bottom layer. So these are the input that we have defined here. We'll have to change this one to make sure that everything stays consistent with what we have defined here. So what we'll do, determine factor of safety. Of course, we first have to make the model. So I'll just call here a function make model. I'll just give the same input parameters because that's actually where we need all the parameters. So let's jump to the function make model. And then we have to, first I want to create the geometry such that I will get back the polygons of the top and bottom one. So let's call this make geometry, which I prepared already a little bit here. Make geometry. First we have to determine the polygon shape. Now already specified here, this should be not D but H to be consistent with the Taylor charts. So if we look at the width of the slope, so I call it W underscore slope, it is H, this H times the slope. This gives us the width. Now if you look at the horizontal coordinates, so the X coordinate, I will make our left boundary, I will set in this case 1 to 0. If I circle back to our PowerPoint presentation, I'll start here. This is the first X coordinate, then I want to move to the toe of the slope, then to the crest of the slope, and then define the right hand side boundary. So back to Site and Plaxis 2D. So then, because these are just needed for internal definition of the parameters, so here we're going to go for the X left, then at the X for the toe of the embankment, it should be X left plus the width of the slope. If you look at the crest of the slope, it's actually 1 times the width to the right hand side compared to the toe. So it will be X of the toe plus the width of the slope. And if you look at the right hand side of the model, it will be X crest plus the width of the slope, because that's what we assumed here to do. Okay, so we have defined these horizontal coordinates. We make this one in the structures mode. So actually we're here going to do gi.go to structures. And we're going to make the polygons here. First I will make the top one, and we'll start at the bottom left and we go counterclockwise. So I will just call it top points, and we'll make that a list. And I'm going to append all the X and Y coordinates for each of these items. I'm just going to compare this. So actually, the first one, of course, here we start at the left-hand side and we start at an elevation of 0. We just assume that the top soil layer has its bottom at the elevation of 0, just for easy reference in this case. The next part that we'll have, we'll move from the bottom left, and we'll move to the bottom right. So X right, and we're going to move to 0 as well. The next point that we'll have, we're going to add the X right hand side, but now we're going to move to the top of the soil layer. In this case, we'll use top layer here, top layer, and as we defined, if I scroll a bit down, the layer thickness we defined here in this dictionary with the key L. So we also have to define here L in this case. The next point that we have, we move to the crest of the slope, and actually this is still all at the top of the soil layer. And now we're actually going to follow the slope downwards. So it will be here at the X of the toe. It will be in the top layer L, but minus the slope height. And then we're going to circle back to the left-hand side, and we're going to also add this one here. So we have to find all the coordinates for this polygon, and so we're going to run gi.polygon. So with gi we tell please operate with Plaxis input, and we're going to use the polygon command, and actually I'm going to send all the top points. I'm going to comment this out, so we're just going to check actually if it works. So here from the tools menu we can do go, and let's see. Oh, I have to. Here it gives me an error in line 75. So what does it say? It says here. The reason is that here we have a function which doesn't do anything. So I'm just going to add the pass option here, such that actually nothing happens in this function. So now it's all. If we can also do here tools and we do a syntax check for Python, everything works out okay. So now we can run it. Let's see what happens. Yeah, I changed the parameter d. It says it's not defined. So let's go here. You can see here actually we have to change the d to h, which is the change I made to make sure we're consistent with the tailored chart parameter definition. Okay, let's run it again. And you can see here that actually we have the top soil layer being generated. Now we can also do the same thing for the bottom polygon. So let's call them bottom points. It's also a list. And actually we're going to use the reuse a bit of. So I'm going to do bottom points append, and again we have to add x and y coordinates. So the first one, since we're also going to go bottom left counterclockwise, I will start with x left, and in this case the bottom is at minus the layer thickness of this one. So it's called bottom layer L. Then we're going to move to the x right, and again minus bottom layer L. So we use again the dictionary key L for the layer thickness. Now then we're going to move to the top of the layer, which is at elevation 0. And at the end we're going to again move to the right hand side. And I'm going to gi.polygon bottom points. Okay, but as you can see here, we generate in the last round of we added the polygon with all the coordinates here. You can see it added two items, polygon 1 and soil 1. If we look sort of generate this one, this is polygon 1. And then here one of the user features of this one is soil 1. So actually we're going to collect this because we want to reuse this one because we want to assign materials to it. So here we say top polygon and top soil. These are assigned by this polygon command. And the same thing, bottom polygon and bottom soil is this one. And we're also going to return these two polygons so we can reuse them in our material. So just do a quick test run to see what we get. Oh, I made a small mistake here. And actually I have to add here the brackets because we're going to append a list of two parameters here. So it has to have the square brackets inside as well. So rerun the command. And it says bottom point is not defined. I used an underscore here, which of course should be clear. So it must always be clear and precise when programming. So if you now rerun this, we have now generated this one, but what I see is that we start building on the already existing material. What we will do in our function, we're going to call si.new, and with that we will start a new model. So let's see. So you can see we have now generated two soil polygons based on the input parameters that we gave. So that goes quite quick. So after making the model, we want to assign the materials. Now, so I create based on the input that we have from these different layers. We have inputted the name of the material, the Young's modulus, the undrained shear strength CU, and the self-weight or the unit weight. So we have made a material for that. So the make soil material is a new function which we're going to convert the info that we have. So I'm going to move this a bit to the side so we have a clear, better view. We will, and then I will also go back to the. So this part that we've covered. The next one would be to create soil parameters. We have the CU and the undrained and the unit weight. What we'll assume for this case, that just also according to what Taylor has defined in his charts for cohesive materials, is that we assume only stability, no deformations, only short term and no consolidation. In that case, we can use more column with the undrained B material type. If we have finite elements, we also need stiffness. We also need the stiffness, which is usually our Young's modulus. The only thing is that the Plaxis command line needs the shear modulus, and this is a consequence of that the internal data structure sent to the calculation kernel is based on the shear modulus and Poisson's ratio, and it's not based on the Young's modulus. So if we want to use Python scripting, we also have to tap into that requirement. But fortunately, with Hooke's law, we can quickly convert the graph to our we can convert our Young's modulus to a shear modulus. So what I will first create is a function to generate soil material and then return this new generated soil material, and then we'll assign it to a polygon. So let's do that. So here we have the Moore column undrained B, and our dictionary contains the undrained shear strength, the gamma and E. So we'll do here we assume a Poisson's ratio of 0.3, and normally for Moore column it varies between 0.3 and 0.35 for a material with undrained A or B, or a drained material. So in this case we'll just assume 0.3. Of course, we might also extend the input of the soil layers with this, but okay, in this case we just assume 0.3 here. The soil model that we choose here is Moore column. So for that one we need to use the number 2. As I said before, for hardening soil you have to choose 3, and for other soil materials you have to choose a different number. For the drainage type, so that means we want to, for instance, use drained or undrained A, B, C, or non-porous. In this case we assumed undrained B, and then we can use number 2 for that. Here we can also calculate our GREF. We just apply Hooke's law here. So here we have the soil info E, and that means here we put the Young's modulus and we divide it by 2 times 1 plus nu. Then we have the soil parameters. We have to give it the material name. This gives us from the soil information. The soil model, we set it here to the parameter here. The drainage types we set to number 2 in this case, based on this parameter. We have to set the weight. Now, the input of undrained B requires that we have to input the unsaturated soil weight and the saturated soil weight. So gamma unsat and gamma sat. We both set it to the same gamma value here. GREF is the input. So this is what we calculated here. Nu is what we defined here. And our undrained shear strength, Cu, we have to specify it with the CREF parameter, and we get it from the soil info as well. Then we're going to execute this one on the soil mod command. So with GI we tell Plaxis use the soil mod command with these parameters, and that will create a new soil material which we will return. Now if we then go back in the make model, so first we use the make soil material to create the material for the top layer, and then we're going to use the top polygon .soil.material. So we assign this top material to the soil of the top polygon. And we can do the same for the bottom material. So we use the same function here, and that generates the new soil material for the bottom layer, which we then have the new bottom material, and we apply this and assign this to the bottom polygon soil. So let's see how that looks like. So this will actually all be executed when we run this. So with F5 we can run it quickly. We can also use the tools option, but if you use it frequently, then the F5 key will do that. And create, as you can see quickly, it generates here a new soil material. And if we look here at the created one, so let's see the material data set. It's Moore column undrained B, what we set. Gamma is set to 20, and for the parameters, our Young's modulus is set to 5000 with a Poisson's ratio of 0.3, and our undrained shear strength is set to 50 kilopascal. So that works. So that's good. Now after we have done that, after the geometry and material assignment, there are a few steps to run the calculation and get a factor of safety. Now step 1 will be to, of course, first we need to generate the finite element mesh. When that's done, we have to go to the stages mode, where we start the initial phase. We activate all the soils there for the gravity loading phase. Then we add the safety phase. We also start the calculation, and then we're going to read the results. In this case, we're not going to start the output program to get all the required results. In this case, the input program also offers some of the basic output already, and we can reach the sum MSF value that we get from the analysis. We can assume that to be the factor of safety in this case. So let's do this step 3. Back to Society and also show Plaxis at the same time. So after we in the main function determine factor of safety, what we'll do, we call it mesh calculate and read results, which is the function here. First step will be to generate the mesh. I say gi.go to mesh. So this is the command that we need to go to the mesh mode. And then I will just generate the finite element mesh with this option here. Next step will be to set up the calculation. So we go to stages. So this is the command to go to stage construction mode. And then we're going to start setting up the initial phase. So the initial phase in this case is gi.initial phase. And we want to change the calculation type. In this case called deform calc type. We set it to gravity loading. This is needed because we cannot use a cannot procedure because we're dealing here with a relevant slope here, such that we have stress rotations just based on self-weight of the material. What's next? We also need to, of course, activate all the soil here. Only the soil generated by a borehole are automatically activated, but in this case we don't have that. So here we just call the activate command, gi.activate, and we say gi.soil. So we just want to activate all the soils that we have. We just have these two soil layers. In this case it's relatively straightforward. And we want to activate this one for the initial phase. Now, after that is done, we want to run the we want to add a new phase. For that one we need the phase command. It's called so gi.phase. With gi Plaxis we tell Python please send this phase command to Plaxis, and we want to get a new phase after the initial phase. So that's nice, but we of course we want to get the so this will create a new phase, and that also returns. So in Python scripting you also get a new phase returns. So I'll just call it safety phase. Just copy it here so we can quickly reuse it. So the new safety phase that we have, we want to change the deformation calculation type to be set to safety. And what we also want to do, we also want to change the name that we see. So in the Phase Explorer, we also want to see the name actually being changed. Identification. And we change it to factor of safety. I'll add two options here because if I run this with the default settings, it will do a very long calculation time. It will take 100 calculation steps. But I don't want to do that in this case because it's not needed for this specific case, and it might make the calculation a bit longer for this demonstration. So for that one I will have to change the default iteration parameters. I will not use the default ones. So first I have to set that one, and I have to change the number of maximum steps. I will set it to 50 in this case. So before I start calculating, let's see how good everything looks. I'll just run the script. I hit F5. And you can see it generates the model, and I can generate the mesh, and it's already done. So let's see what we have here. If I just make the model a bit bigger. So we have the initial phase. Everything is activated here. Factor of safety. And if we look at this factor of safety, we can actually see here that the use default iteration parameters is switched off, and the maximum step set to 50. So that looks good. Next step would be actually now to start the calculation. And after we run the calculation, there's a special option in the safety phase. We have a special object called reached that contains a few of the reached parameters, or the main parameters of the calculation. That can be sort of the end time of this, but also this sum MSF parameter. So we're going to obtain this one, and then we're going to return that one from this function. So that means that here we get this one as well, because that's returned by the mesh calculate read. And then I'm also going to return this, so that my function determine factor of safety actually is going to return this factor of safety number. Now what's nice then is that in this case here we can also print all the information. So I made here a print of the information of the slope with not with T but with H and L, and then it gives us the factor of safety. So let's see what happens here. I hit F5. So it will generate a model, generate a mesh, set up the phases. Now you can see it starts the calculation. And it will do here the factor of safety calculation. And apparently I made a small mistake. It says here return FOS, but FOS is not defined. It seems I misspelled here. Python is case sensitive, so I'll make sure that everything where we use this factor is actually going to be correctly used. So I hit it again. You can see it runs fairly quickly. By just hitting F5, it quickly sets up the model, runs the initial stage, and then also runs the safety phase. And now it should work. After 50 calculation steps. And again, apparently I added D here. So let's make sure that this one is also set to H. I'll rerun it. Now if we look back a little bit, is that we get the factor of 1.39 from this analytical solution. And Plaxis looks to be still calculating. Oh, it's now done. And let's see what our result is. So slope 1/2 with H is 12 and the layer thickness is 16. The factor of safety is 1.38. So that's quite close to the result from the original Taylor chart. But what would be nice to see, so let's make sure that we can also read it in this small box at the side. So say that we change the slope angle to 3, and let's see what we get here. So actually we'll make the slope less steep. You can also see here, and you can see here also it's been generated. It looks less steep compared to the other one, so this is 1/3. I'm going to quickly run the calculation, and we can see now from this analysis that actually we're also going to see that the factor of safety is 1.67. Or if we want to do another variation, instead of the slope 2, we set the thickness of the height of the elevation, we'll make it 14 and 1/2, and then we're going to quickly run the analysis. And here we see again quickly generating the model. If we screw this a bit to the side, you can see here that we still have this 1/2 slope, but this is not as high as well. And you can see actually here that the factor of safety here is 1.3. So actually, because we excavate here, for instance, the slope for a bit deeper, we actually get a lower factor of safety. So this is a quick way to sort of quickly parameterize the input for such a slope stability analysis. So that's actually relatively easy to do. But then comes the next step. You made a very nice script for automation, and then the thing is how to share your script. Of course, you can just give somebody else the Python script. You develop this one, and then you want to share it. But then the colleague says, oh, I don't want to use programming. I'm not familiar with this, I don't want to use it, I don't want to learn it, I don't have time to learn it, or any reason that they don't want to use it. A nice solution is that we can directly run it from menu item in Plaxis. And as a result, we get an automated workflow for everyone, which of course will enhance the productivity within the office and within your colleagues. That's nice. So how to do this? There are a few challenges, of course. Everybody needs to have a Python distribution. Needs to have a Python distribution on his machine. Now, Plaxis already solved it by installing this into the Plaxis in the installation folder. So there we already have a Python distribution. So that's already covered up. Then what I also showed at the beginning, we have to set up the communication. We have to have a port and a password. Now we can these will vary typically on different computers, especially the password, which is automatically generated by default. Everybody can use the same password, but not everybody wants to use that one or wants to rely on this password. So there we already came up with a solution for this one. So how do we share this? Now, what we do, we write our code in Site, we test to make it work, and then we're going to update the boilerplate. In this case, we will not add any parameters to the new server. And then when you call the Python script from within Plaxis, Plaxis will start the Python script on the command line such that it will also pass the relevant port number and password to it. What's optional, we can copy this to the PyTools folder inside the Plaxis installation folder, and then we can directly access it from the menu items from Expert Run Python tool. So I'm going to make an example, and we're going to add a safety phase after each consolidation stage. I will build this starting in Site, test the code, change the password, which will make sure that it fails to run because we still have the old password there, and then we'll change the code in Site to try again. So let's start doing this. Let's start Site and input, and of course we need to have a model, which we'll call this one. So here we have a model. If I just make this a little bit bigger, it's also an embankment problem. And here what we see is that we get, if I can make this a bit bigger, I'll just show it like this. So here are a bunch of consolidation stages, and after every consolidation stage we want to add a safety phase. Now, you can see there are two plastic phases, phase 13 and 15, and actually we don't want to have a plastic, we don't want to have a safety analysis after this one. Okay, so we'll start the new phase, a new one. I'm going to hide the output while we write this one. Or actually, I'm going to keep it. First, we need to have the boilerplate. I'll just copy it from this one. So what do we want to do? So we want to get for all the phases. So what we'll do, we'll make a for loop for a phase in gi.phases, and then I'm going to make a copy of this list in Python, and we can use this with these square brackets, semicolon here. Then we have at least a copy of a static phases list. Otherwise, due to internal operations, while adding more phases, this list will change during the runs, which we don't want to have. Then the next step would be that we want to check if the phase.deform calculation type is actually consolidation. If that's the case, we're going to add a new phase. So we'll call a new phase is gi.phase. That's the same thing we used in the last example. We're going to add a new phase after this phase. So this is the phase that we get here from the loop over all the different phases. And this new phase, we want to set it to deform calc type is safety. Very nice. Now, what's also nice with Python, we can have some kind of interactive reusing data. So I'm also going to rename the phase, and I'm going to say new phase dot identification is, I call it factor of safety, and I'm going to reuse the name of the phase where it starts from. So what you just, since we know it's phase, there's the parameter phase, and we call it identification. Let's make it a bit bigger so we can see the full script. So here we just make a Python string, and we're going to format this using the identification. Okay, now this should work. I'm going to have to save it. File, save as. And where I'm going to save it, I'm going to, so here I have, let's go to my Plaxis installation folder. Now there's a special folder called PyTools, and it's for input. So I'm going to give it here is that I'm going to do consolidation safety. And I have to add the extension .py such that Society will understand it's a Python script. Here we go. So I'm going to use this one. And let's see what happens. I'm going to expand this a little bit so we can better see what's going on in this list here. Let's put it a bit here to the side. And then we're going to run this one. So I'll do tools go, F5. And it's going to add a lot of phases here. And you can see here it adds more phases and also changes names here. And you can see here it says, for instance, let's look at this phase. Factor of safety, consolidation after A. Now this is the phase 2, consolidation after A. And actually this is the factor of safety calculation that starts from that one. So with this one we can quickly add all these models. So if I just going to go back to the situation where we don't have the safety phases. So let's make this a bit bigger. Now you can see we don't have any safety phase. We can see here on the icon that we just have consolidation and plastic phases. Okay, so we have this one. Oh, I lost my thing here. So now what we're going to do from expert run Python tool, here we have the consolidation safety. Let's see what we get when we share this with another user, with one of our colleagues. So we say run Python tool, consolidation safety. He has to activate the remote scripting server. Now, he might have a different password. So here we say different password. And we're going to start the server and we'll see nothing happens. Now, the reason for that is, and we don't get feedback. That's of course the downside if we run it like this. But the thing is here in our script, we still have the old password. Now, as I said before, we can just, if we run it like this, so here we going to remove, I will do like more like this. So I'm just going to initialize the new server here. With this command, I'm not going to use the old situation. I'm just going to do this. If I run it from here, it doesn't work because it still needs a port number and password. That doesn't work. But if we now run it from here, expert run Python to consolidation safety. Let's run it, see what happens. And you can see here we have all our safety phases here. So that's also a quick way to share your script, your Python script with your colleague. What you then do is that you, if I make this a bit bigger, So this is the original boilerplate to initialize the contact with Plaxis. In this case, you're just going to remove all the parameters from the new server function, and with that, by running it from Plaxis input, it will automatically fill the data for you. So that's also a quick way to do this. That brings us to the end of today's presentation. I showed you using the commands runner, macros. I set up a Python script for parametric slope stability calculation. At the end, we used under 100 lines of code, so it was not that much of code that we need to use for this. And then we had a parametric code for slope stability analysis using strength reduction method. And finally, I showed you a way to how you can share Python scripts with your colleagues without any programming. Of course, you have to initially use programming to set it up, but then you can just share it with all your colleagues to make easy usage and without any programming experience.